The following video, we are going to start solving trig equations. We have 8 examples in this video and 6 in the next video. So solving trig equations, essentially what we're doing is we're working backwards and we're going to figure out what angle makes this work. So tangent squared theta plus tangent theta equals 0. I know that my answer has to be between negative 90 degrees and 90 degrees. And in a lot of these problems, we end up with more than one answer because more than one angle makes this thing work. So I'm going to use all of my algebra understanding and knowledge. Uh, I'm going to factor out a tangent theta because there is a greatest common factor. So I have tangent theta pulled out, and then I still have tangent theta plus 1 equals 0. Now I set both parts of this equal to 0 by the zero product property. So tangent theta equals 0 and tangent theta plus 1 equals 0. So what I'm looking for is where tangent theta equals 0 and tangent theta equals negative 1. So ultimately what we're doing now is we're figuring out where does tangent theta equal 0. Now tangent is on our unit circle y over x. So where is y equal to 0? Y is equal to 0 in those two spots. So because y is equal to 0 in those two spots, I need basically 0 degrees. Remember, my answer is going to be in degrees here. 0 degrees or 180 degrees or negative 180 degrees or something like that. Now, since we're only going from negative 90 to 90, the only answer that works in this case is 0 degrees. Where is tangent of theta equal to negative 1? Tangent of theta is equal to negative 1, where y over x equals negative 1. And so y over x is equal to negative 1 at 45-degree reference angles in the second and fourth quadrants. Since it's from negative 90 to 90, we're only going to look at the fourth quadrant, and we're going to say negative 45 degrees. So tangent of theta equals 0 degrees and negative 45 degrees are the two answers that we have for this problem. Number 2, sine of 2x equals sine of x. So conceptually speaking, what we're trying to figure out is what does x have to be for the sine of that angle to equal the sine of double that angle? So that's kind of conceptually what's happening. But we can also use a property that we know about the double angle of sine. So sine of 2x is equal to 2 sine x cosine x. Now I'll subtract sine x from both sides and set it equal to 0. And now I have a very similar situation in number 1 where I have a greatest common factor. So sine of x times 2 cosine x minus 1 equals 0. So now I set both parts equal to 0. I get sine x equals 0 and 2 cosine x minus 1 equals 0. When I solve that, I add 1 and divide by 2, and I get cosine x equals 1/2. So now what I have to do is figure out where does sine of x equal 0. Sine of x equals 0 at 0, pi, 2 pi, all of those things. Notice I'm in radians here, and I have brackets, so that means that I have to include 0 and 2 pi. So x must equal 0, pi, and 2 pi. Now let's figure out what happens when cosine of x equals 1/2. Cosine of x equals 1/2 when I have this situation, but that can occur in both the first and the fourth quadrants, because it doesn't really matter whether our y on our unit circle or y on our circle is positive or negative when cosine of x equals 1/2. So I actually have two situations where this works. I have pi thirds and 5 pi thirds. So I have 5 answers that make this work. Conceptually speaking, what's happening is when I plug in pi over 3 to the original, sine of 2 pi over 3 does equal sine of pi over 3 because sine is positive in both first and second quadrants, and that reference angle is pi over 3. And that would work for all 5 of the things that I would plug in. I'd end up with sine of 2x equaling sine of x. So since x had to be between 0 and 2 pi, these are the 5 answers that would work between 0 and 2 pi. Number 3, I'm going to add 2 to both sides. So I have 2 cosine squared x minus 5 cosine x plus 2 equals 0. And then I have more factoring. So 2 cosine x, and then figure out where the 2's go. So this is a minus 2 minus 1. Notice if you were a little confused as to where I got that so fast, if I had 2a squared minus 5a plus 2 equals 0, you would probably be able to factor that into 2a minus 1, a minus 2 pretty quickly. Well, I'm just replacing a with cosine x. So this is essentially something that's quadratic looking. And when something is quadratic looking, I can end up doing something like that. So now I set both of these equal to 0. I get cosine of x equals 1/2 and cosine of x equals 2. Notice that cosine of x equals 2 is impossible because the radius can never be bigger than the x value in the unit circle, or it can never be smaller than the x value in the unit circle. And cosine is x over r in the unit circle. So cosine can never be bigger than 1. That doesn't make any sense. Cosine of x equals 1/2. We actually just did this. We found that it was pi over 3 and 5 pi over 3. But notice that in this problem, we have negative pi to pi as our domain. So because that's our domain, x equals pi over 3. And then 5 pi over 3, I have to convert it by subtracting 2 pi from it, because 5 pi over 3 here is in the exact same spot. It's coterminal with something when I subtract or add 2 pi to it. So when I subtract 2 pi, I get negative pi over 3, which is in our domain, and that's our answer. Number 4, sine squared equals cosine squared, and my domain is from 0 to 360. What I'm going to do here is I'm going to subtract cosine squared to the left side. I could have subtracted sine squared to the right side. Either one would have been fine. This is just the one I chose. Now, this is a little bit complicated, but if I remember that cosine squared is equal to 1 minus sine squared, now I can get everything in terms of the same trig function, and that's often what I'm going to want to do. So I end up with 2 sine squared minus 1 equals 0 when I distribute the negative sign. So I have sine squared plus sine squared minus 1, and then this ends up working out. So sine squared of theta equals 1/2. Then I square root both sides. Now remember, when I square root, I'm going to take a plus or minus. So I have plus or minus the square root of 1/2, which is plus or minus root 2 over 2, when I use a FFU in order to get there. So now where is sine root 2 over 2? Sine is root 2 over 2 at pi over 4 or 45-degree reference angles. And it's the plus or the minus cases. So I actually end up in all 4 quadrants because I have the plus or minus. So in this case, theta equals 45 degrees, 135 degrees, 225 degrees, and 315 degrees. Number 5, 2 sine x cosine x equals cotangent x. What I'm probably going to do is rewrite cotangent as cosine over sine. Now notice that sine's in the denominator. So I have a domain of x to be between 0 and 2 pi. The problem with that is that there are certain values of x that will make the denominator 0 and make this undefined. And excuse me, I can't have something on the left side be defined and on the right side be undefined. That doesn't make any sense. So where does sine of x equal 0? Sine of x equals 0 at 0, pi, and 2 pi. So x cannot equal those 3 things. If x ends up equaling those 3 things, it doesn't make any sense and it won't work out. So I'm going to multiply the sine over. So I have 2 sine squared x cosine x equals cosine x. Then I'll subtract the cosine x over. So I have 2 sine squared cosine minus cosine. Now notice I have a greatest common factor of cosine. So I will factor that out. And now I can set both parts equal to 0. So cosine x equals 0. And sine squared x, add 1, divide by 2, equals 1/2. Notice that I just did sine squared equals 1/2. So I know what the answers are for that. So sine x equals plus or minus root 2 over 2. So x equals pi over 4 3 pi over 4, 5 pi over 4, and 7 pi over 4. Then cosine of x equals 0. Well, I'll draw a little picture. Cosine of x equals 0 when x equals pi over 2 or 3 pi over 2. And so what I end up with is 6 answers within 0 to 2 pi. And notice none of those answers were 0 pi or 2 pi, so I can keep them all. We'll skip number 6 until the end of the video. But in order to understand the next concept that we're going to talk about in problems 6, 7, and 8, I want us to go to these problems real fast. Notice that in these problems, the domain no longer is something between 0 and 360 degrees or negative pi to pi or something like that. It's talking about all degrees or all radians anywhere. And so when we look at that sort of situation, we kind of have to understand what's going on. So we know that sine of x equals 1/2. Just in a degree situation, let's pretend like we're going from 0 to 360. In that case, sine of 1/2 would be equal to x would be 30 degrees or 150 degrees. And likewise, in the radian format, it would be pi over 6 and 5 pi over 6. So what this is saying, if it's any value of degrees, is if we're looking at what's happening in a sine situation, sine is 1/2 at 30 and 150. We can't just restrict it to between 0 and 360. We also have to look at every single possible coterminal angle that there is. So if I add 360 a bunch of times, or if I subtract 360 a bunch of times, I end up with a bunch of different answers that are all the same, or that all give me sine of x equaling 1/2. So for example, 390, 750, and so on in the positive direction, negative 330, negative 690, and so on in the negative direction. And that would also work for 150. So if I added 360, I'd get 510, 870, and so on. So I end up with a lot of different answers that end up working out. So basically what I would do in this case is I notice that 360 degrees or 2 pi is the period of this function. And so what I do is I take the answers that I get, and when I have degrees as like all degrees, I would take whatever answer I get and add 360 times n being an integer. So I have a new answer for degrees. It would be x equals 30 plus 360n, and x equals 150 plus 360n, where n is an integer. Likewise, I would do the exact same thing for sine of x down here. So x equals pi over 6 plus, notice the period is 2 pi, I would say 2 pi n, and x equals 5 pi over 6 plus 2 pi n, where n is an integer. So what happens is if I have degrees or radians, then I end up cycling through and just getting every single coterminal angle that I possibly can for those problems. If I have tangent of x equals 1, it's a very similar situation. I would know that this is true in the first and third quadrants, so I would get 45 degrees and 225 degrees as my answer, or pi over 4 and 5 pi over 4. Well, what would happen is all the coterminal angles would end up cycling through, and I would end up getting 45 plus 360n and 225 plus 360n, and that would work for this. But notice that the period of tangent is actually a 180 degree or a pi length period. And well, if I actually look at this, 145 and 225 are actually 180 degrees apart. And then if I kept adding 360 to both of those, I'm just going to get every single angle that's 45 plus 180n. And that makes sense because the period is 180 degrees. So if I were writing tangent of x equals 1 in radians, where I get all radians possible ever, I would say pi over 4 plus pi n, where n is an integer. And that is a terrible box. So that's kind of how this works if I have to find every single value in radians or every single value in degrees. So let's start with problem 8 and then kind of work our way backwards. So problem 8, well, this x minus 57 is kind of weird. So let's just pretend like it's cosine of theta equals -1. Well, cosine of theta is equal to -1 at 180 degrees. And that would also be true since we're dealing with every single possible degree. I would be going plus 360 times n, right? So that's kind of what's happening here. I'm going to continually add or subtract 360 a bunch of times, and then I'd get every single possible degree. Well, in this problem, it's saying x minus 57 equals 180. So my x value is actually 237 degrees. Because if I put in 237 minus 57, then I end up getting 180. So what I have to do for this is I would say x equals 237 plus 360n, because I can keep adding or subtracting 360 from 237 and plug it in for x, and then I would get the right answer. So this would be true if I were dealing with any possible degree value. Problem 7, we're going to do the same type of thing, except we're going to be dealing with radians. I'm going to convert this cosine squared into 1 minus sine squared. And then I have 1 minus 2 sine squared equals sine. I'll get everything on the right side of the equal sign. So I have 2 sine squared x plus sine x minus 1. And if I look, this is quadratic in form. So I have 2 sine x sine x. And then I kind of have to figure out where these ones go in the plus and minus signs. So I have plus 1 over here, minus 1 over here. So I end up with 0 equals sine x plus 1, and 0 equals 2 sine x minus 1. So sine x equals -1, and sine x equals 1/2. Now I should know these pretty simply. I end up with sine of x equals -1 when x equals 3 pi over 2, and sine of x equals 1/2 when x equals pi over 6 and 5 pi over 6, which we already talked about in the last problem. Now, notice I have 3 possible answers here. Sine of x, or I'm sorry, x equals pi over 6, 3 pi over 2, and 5 pi over 6. And the period is 2 pi. So x equals pi over 6 plus 2 pi n. X equals 3 pi over 2 plus 2 pi n. And x equals 5 pi over 6 plus 2 pi n. So I end up with 3 possible answers, and they keep cycling through every 2 pi. Finally, let's go back to number 6, where I have 2 cosine 2x plus 3 minus 1 equals 0. If I solve for the cosine part, I add 1 and divide by 2 to both sides. So I have cosine of 2x plus 3 equals 1/2. Really quick, let's just think about it as what would happen if it was just like cosine of theta. So if cosine of theta equals 1/2, we know that's at pi over 3 and 5 pi over 3 in radians, but since we're in degrees, I know that that is 60 degrees and 300 degrees. So I know that that would be true in that particular case. Now, since theta is really 2x plus 3, I need 2x plus 3 to equal 60 and 2x plus 3 to equal 300. So when I solve these, I get x equals 57 over 2 and x equals 297 over 2. Now, if it were just between 0 and 360, I would probably think I was done. But I also have to be really careful in this problem because what is the period of this function? Well, when we were graphing these things, I would remember that if I had something like cosine of 2 times x minus pi, I would know that I would have a right shift of pi, and then my period would change. So if I had a 2 in there, really my period is pi. So in this case, when I have this 2 inside of the cosine, my period would be pi because my normal period's 2 pi, but I have this period stretch or shrink. Since it's in degrees, my period is no longer 360. My period is now 180. So I have 57 over 2 plus 180n and 297 over 2 plus 180n. And that ends up being my final answer for that problem.